May 16th, 1940. The morning mist clung to the farmland south of Calais like artillery smoke that refused to disperse. Pilot Officer Bill Caister fought his damaged Spitfire through another violent shudder as the Rolls-Royce Merlin engine coughed black smoke across the English Channel. Coolant temperature climbing past the red line, oil pressure dropping with each laboured revolution. The 27-litre V-12 that had carried him through 12 combat sorties was dying. 3,000 feet below, occupied France waited with its Wehrmacht banners and anti-aircraft batteries. Caister knew the mathematics of engine failure with brutal clarity. The glycol coolant, streaming from his punctured header tank, meant perhaps 90 seconds before thermal seizure transformed his fighter into a gliding coffin. No altitude for a glide back to England. No options except the field spreading beneath him like a chessboard designed by his enemies. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Spitfire touched French soil at precisely 08:15 hours, wheels down on a farmer's field that would become coordinates in a Luftwaffe intelligence report. German soldiers surrounded the aircraft before Caister could destroy his maps and codes. But the Merlin engine, still ticking as metal cooled in the spring air, represented intelligence far more valuable than any tactical document. Within 4 hours, a Wehrmacht transport truck carried Spitfire Mark I, serial number X4260, toward Erprobungsstelle Rechlin, the Luftwaffe's premier testing facility, 100 kilometers northwest of Berlin, where Germany evaluated every captured Allied aircraft that could be repaired to flying condition, where engineers dissected enemy technology with Prussian thoroughness, where uncomfortable truths about British aviation sometimes emerged from systematic analysis. Oberingenieur Klaus Richter stood in Rechlin's engine workshop 3 days later, leather notebook in hand, slide rule clipped to his breast, pocket. At 42, Richter had spent 18 years perfecting German aero engine design. Daimler-Benz invited him to consult on the DB600 series development. Junkers requested his analysis of supercharger efficiency. His technical papers on metallurgy and thermodynamics filled university libraries. He approached captured British engines with professional skepticism refined by ideological certainty. German engineering represented precision perfection. British manufacturing emphasized mass production over theoretical elegance. The Spitfire's engine would confirm what Richter already knew about Allied industrial limitations. The Merlin Mark III sat on its test stand like a mechanical puzzle waiting to be solved. 27 litres of displacement packaged in an aluminum block that weighed only 650 kilograms. 12 cylinders arranged in a 60-degree V configuration. Each bore precisely 137 millimeters. Richter's first measurements challenged fundamental assumptions about power-to-weight ratios. Our Daimler-Benz 601 generates 1,350 metric horsepower from 33.9 litres, Richter murmured to his assistant, Lieutenant Karl Bauer. This British engine produces 1,310 horsepower from 27 litres. The specific output exceeds our designs by nearly 20%. Bauer recorded specifications that seemed deliberately wasteful by German standards. Dual magnetos firing twin spark plugs per cylinder. Redundancy that added complexity without apparent performance benefit. Sodium-cooled exhaust valves requiring specialized metallurgy that German suppliers struggled to duplicate. Single-stage supercharger driven through fluid coupling that allowed automatic adjustment based on altitude and manifold pressure. German engines use mechanical supercharger drives with fixed ratios, Bauer observed, his pencil hovering over calculations that refused to reconcile with Luftwaffe doctrine. This constant-speed hydraulic coupling maintains optimal boost across the operational envelope, automatic altitude compensation without pilot intervention. Richter examined the supercharger installation with growing professional unease. The centrifugal impeller spun at 28,000 revolutions per minute, driven through a hydraulic coupling that eliminated the mechanical shock loads plaguing German variable-speed drives. Rolls-Royce engineers had solved supercharger control through fluid dynamics rather than complex gearing. Simpler, more reliable. Theoretically inferior, yet practically superior. The fuel system revealed British engineering priorities that contradicted German assumptions about combat aircraft design. Two SU carburetors fed the induction system through a manifold designed for even fuel distribution across all 12 cylinders. Conventional technology that German engineers had abandoned in favor of direct fuel injection. Yet the Merlin's carburation delivered consistent mixture ratios that Junkers' technical manuals claimed were impossible without injection. The negative G problem, Bauer said quietly, referencing intelligence reports from Battle of France engagements. British pilots cannot follow our fighters into dives because their carburetors flood under negative acceleration. Their fuel supply interrupts. Our Messerschmitts escape through superior engineering. Richter nodded, understanding the tactical advantage German fuel injection provided in combat. Messerschmitt Bf 109 pilots could push their noses down into vertical dives, knowing their DB601 engines would maintain full power under negative gravity loads. British fighters had to half-roll inverted before diving, losing precious seconds that meant life or death in aerial combat. But temporary advantage through one technological choice did not excuse the Merlin's remarkable power density. Richter's calculations revealed engineering achievements that German industry had not matched despite years of development and unlimited resources. The British had created an engine that weighed 40% less than the DB601 while producing equivalent power. Specific output per kilogram exceeded German designs through metallurgical sophistication that Reichsluftfahrt Ministerium suppliers could not duplicate. The cylinder head construction, Richter announced, removing the aluminum castings for detailed examination, utilizes aluminum alloy with thermal conductivity exceeding our standard specifications. The British source superior materials that permit higher operating temperatures without deformation. Each cylinder head contained 2 intake and 2 exhaust valves, operated by a single overhead camshaft through rocker arms running on needle bearings. German engines typically used single valves per cylinder to minimize complexity. The British had accepted mechanical sophistication to maximize gas flow and combustion efficiency. 4 valves per cylinder meant better cylinder filling at high engine speeds, better scavenging of exhaust gases, higher volumetric efficiency that translated directly into power output. The valve timing specifications, Bauer calculated from disassembly measurements, permit engine operation at 3,000 revolutions per minute. Our DB601 operates at 2,600 maximum. The British achieve higher power through increased rotational speed rather than displacement. Richter understood the implications immediately. German engines emphasized displacement and moderate speeds for durability, large cylinders, conservative rotational velocities, long operational life between overhauls. British engines prioritized power density through high-speed operation that accepted shorter service intervals. Different engineering philosophies revealing different strategic priorities. The crankshaft assembly demonstrated manufacturing precision that challenged Richter's assumptions about British industrial capabilities. 7 main bearings supported the forged steel crankshaft, each bearing precisely machined to tolerances measured in hundredths of millimeters. The crankshaft itself had been dynamically balanced to eliminate vibration harmonics at operating speeds. Manufacturing quality that matched or exceeded German peacetime production standards. Bearing clearances fall within 2/100ths millimeter tolerance, Bauer reported, his micrometer confirming measurements that seemed impossible for wartime mass production. The British maintain precision manufacturing despite bombing raids and resource limitations. The supercharger installation revealed the most sophisticated aspect of Merlin engineering. The centrifugal impeller, cast from aluminum alloy and precision machined to aerodynamic perfection, compressed intake air to 14.7 pounds per square inch at full boost. The hydraulic coupling that drove the supercharger used engine. Oil pressure to maintain constant impeller speed regardless of engine RPM variations. Automatic boost control that German engineers had pursued unsuccessfully for years. This fluid coupling eliminates the mechanical complexity of our variable speed drives, Richter admitted, his professional pride battling with objective analysis. The British solved supercharger control through hydraulic engineering rather than mechanical gearing. The solution is elegant in its simplicity. Bauer examined the oil scavenging system that maintained lubrication throughout the Merlin's operational envelope. Multiple oil pumps ensured continuous circulation, even during violent combat maneuvers. The oil tank, pressurized to prevent cavitation at altitude, held 35 liters of lubricant. Separate pressure and scavenge pumps moved oil through passages drilled into every critical bearing surface. The lubrication system includes dedicated cooling passages for the supercharger bearings, Bauer noted. Tracing, oil flow through channels that maintained bearing temperatures within design limits. German engines rely on splash lubrication for accessory drives. The British engineered positive pressure lubrication for every rotating component. Richter assembled performance calculations that documented British engineering achievement with mathematical precision. The Merlin Mark III generated 1,310 metric horsepower at 3,000 RPM and 12,000 feet altitude. Specific output reached 48.5 horsepower per litre, substantially exceeding the DB601's 39.8 horsepower per litre. Power-to-weight ratio favoured the British engine by nearly 30%. The British have created an engine that produces equivalent power to our DB601 while weighing 150 kilograms less, Richter said slowly, his voice carrying implications that extended beyond technical specifications. Their power density exceeds our designs, through superior metallurgy, higher rotational speeds, and more efficient supercharging. The strategic significance emerged through systematic comparison. Luftwaffe intelligence had reported British fighters as inferior to German designs in speed and climb performance. Yet the engine powering those fighters demonstrated engineering sophistication that challenged every assumption about Allied industrial capabilities. If British engines exceeded German designs in power density and operational efficiency, perhaps Luftwaffe tactical superiority resulted from pilot skill and tactical doctrine rather than technological advantage. Bauer completed calculations that quantified the Merlin's operational characteristics with disturbing clarity. Maximum continuous power output of 1,030 horsepower at 16,000 feet. Emergency power of 1,310 horsepower at 12,000 feet. Specific fuel consumption of 0.53 pounds per horsepower per hour, 10% more efficient than comparable German engines. The British achieve superior fuel economy through precise carburation and efficient combustion chamber design, Bauer reported, his engineering training overcoming nationalistic prejudice. Their mixture distribution across 12 cylinders maintains stoichiometric ratios that our injection systems struggle to match. Richter examined the cooling system that maintained Merlin operating temperatures within design limits, despite power outputs that would destroy less sophisticated engines. Ethylene glycol coolant circulated through passages cast directly into the cylinder blocks and heads. A large radiator mounted beneath the Spitfire's wing used ram air for heat rejection. The header tank, positioned at the engine's highest point, maintained system pressure through a relief valve calibrated to 15 pounds per square inch. The pressurized cooling system allows coolant temperatures above 100 degrees Celsius without boiling, Richter explained, understanding the thermodynamic advantages. Higher coolant temperatures improve thermal efficiency while reducing radiator size requirements. The British engineered their cooling system for maximum heat rejection with minimum aerodynamic drag. The afternoon light slanted through Recklin's workshop windows as Richter compiled preliminary findings that would challenge Luftwaffe assumptions about British aviation capabilities. The Merlin engine represented not just competent engineering but sophisticated design that exceeded German achievements in specific power output, operational efficiency, and manufacturing precision. Our assessment must acknowledge British engineering superiority in several critical areas, Richter wrote in his preliminary report. Power density exceeds German designs by 30%. Specific fuel consumption demonstrates 10% improvement over comparable engines. Manufacturing quality matches peacetime German standards, despite wartime. Production pressures. Bauer understood the professional courage required to document uncomfortable truths. German military doctrine assumed technological superiority across all domains. Intelligence reports emphasized Allied numerical advantages, while dismissing enemy equipment as inferior copies of German innovations. Richter's analysis suggested that British engines, at minimum, matched and possibly exceeded German designs in critical performance categories. The implications extend beyond engine performance, Bauer said carefully. If British fighters carry engines superior to our own in power-to-weight ratio and operational efficiency, their tactical limitations must result from factors other than propulsion system inadequacy. Richter nodded slowly, his analytical mind projecting consequences that extended from technical specifications into strategic doctrine. Messerschmitt pilots reported that Spitfires turned more tightly than Bf-109s at lower altitudes. Intelligence attributed this to aerodynamic design, but perhaps British fighters achieved superior maneuverability through lighter engines that improved thrust-to-weight ratios. The negative G advantage we possess through fuel injection remains valid, Richter confirmed, seeking tactical reassurance in mechanical facts. But we must acknowledge that British engines demonstrate engineering sophistication that challenges our assumptions about Allied industrial capabilities. As evening approached, Richter ordered complete engine disassembly for metallurgical analysis. Each component would be measured, weighed, and tested to quantify British manufacturing capabilities. Cylinder head castings would undergo spectrographic analysis to determine alloy compositions. Crankshaft forgings would be stressed to failure to establish material properties. The supercharger impeller would be examined under microscope to document machining precision. The complete evaluation will require approximately 4 weeks, Richter estimated, his professional thoroughness demanding systematic analysis. We must document every aspect of British engine design to provide Reichsluftfahrtministerium with accurate technical intelligence. Bauer began photographing the Merlin from multiple angles, creating permanent records of British engineering that German designers could study. Each photograph would be labelled with technical annotations. Each measurement would be verified through multiple instruments. The analysis would proceed with Prussian precision that refused to allow ideological preference to corrupt objective data. But as Richter locked his workshop for the evening, professional unease troubled his certainty about German technological supremacy. The British had created an aircraft engine that exceeded German designs in critical performance categories. They had achieved this through industrial processes, operating under bombing raids and resource constraints. They had mass-produced these engines at rates that suggested manufacturing capabilities far beyond German intelligence estimates. The morning's casual assumption about British industrial inferiority had dissolved under systematic analysis. Richter faced uncomfortable recognition that Allied engineering, at minimum, matched German capabilities, perhaps exceeded them. The implications would become clearer during detailed metallurgical testing, but the initial examination had revealed enough to challenge fundamental assumptions about the air war unfolding across Europe. Reichsluftfahrtministerium would receive his preliminary report within 48 hours. The complete technical analysis would follow in 4 weeks, but Richter already understood that his findings would complicate German strategic planning. When your enemy builds engines that exceed your own in critical performance categories, numerical superiority becomes inadequate explanation for tactical success. The captured Merlin sat on its test stand in Rechlin's workshop, a mechanical monument to British engineering achievement. Tomorrow, Richter would begin systematic disassembly. He would document every design choice, every manufacturing process, every metallurgical specification. He would provide German leadership with objective technical intelligence, regardless of whether that intelligence confirmed or contradicted ideological assumptions. Because wars were won through accurate understanding of enemy capabilities, not through comfortable delusions about predetermined superiority. The Merlin engine had already revealed uncomfortable truths. The complete analysis would determine whether those truths demanded strategic reassessment or merely tactical adjustment. May 19th, 1940. Klaus Richter arrived at Recklin's engine workshop before dawn, driven by professional curiosity that had troubled his sleep through 3 successive nights. The Merlin engine waited on its test stand like a mechanical sphinx, each component promising revelations about British engineering capabilities that contradicted German assumptions about Allied industrial limitations. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lieutenant Bauer had prepared the metallurgical testing equipment overnight: spectrographic analyzer for alloy composition, tensile testing machine for material strength analysis, precision scales for component weight documentation. Every instrument calibrated to establish British manufacturing capabilities with scientific accuracy. "We begin with the cylinder head castings," Richter announced, his methodical mind demanding systematic progression through engine components. "The aluminum alloy composition will reveal British metallurgical sophistication and manufacturing quality control." The cylinder head separated from its mounting studs with the precise mechanical resistance that indicated proper engineering clearances. Richter examined the casting under magnification, noting the fine-grained structure that suggested careful temperature control during solidification. No porosity, no inclusions. Manufacturing quality that matched German peacetime standards despite British factories operating under blackout conditions and bombing threats. Bauer positioned a small sample from the cylinder head casting in the spectrographic analyzer. The instrument burned the aluminum alloy at high temperature, separating the light spectrum into constituent wavelengths that identified each element present in the material. The results would document British metallurgical capabilities with precision impossible to dispute through ideological preference. The composition indicates aluminum alloy with 4.5% copper, 1.5% magnesium, 0.6% manganese, Bauer reported, recording spectral lines that defined British material science. This corresponds to our understanding of high-strength aluminum alloys for elevated temperature applications. Richter calculated thermal conductivity based on alloy composition. The British had selected materials that maximized heat transfer from combustion chambers to cooling passages while maintaining structural strength at operating temperatures exceeding 200 degrees Celsius. Optimal metallurgical choices that demonstrated sophisticated understanding of thermal management and mechanical properties. The thermal conductivity exceeds our standard aluminum alloys by approximately 15%, Richter observed, his professional assessment overcoming nationalistic bias. British metallurgists have optimized material selection for engine operating conditions. This superior thermal conductivity permits higher power outputs without thermal distortion. The crankshaft removal required careful attention to assembly sequence and component relationships. Richter documented each step photographically, creating permanent records of British design choices that German engineers could analyze. The crankshaft itself, forged from high-carbon steel and nitrided for surface hardness, demonstrated manufacturing precision that challenged assumptions about British wartime production capabilities. Bauer measured crankshaft journal diameters with precision micrometers, recording dimensions that varied less than 0.02 of a millimeter across all 7 main bearing positions. Tolerance control that suggested sophisticated manufacturing processes and rigorous quality inspection. The journals themselves showed careful attention to surface finish, with grinding marks indicating final machining that achieved mirror-smooth bearing surfaces. Journal diameter tolerances fall within plus or minus 1/100th millimeter, Bauer announced, his measurements confirming manufacturing precision that exceeded minimum functional requirements. The British maintain dimensional control comparable to our peacetime production standards. This suggests dedicated manufacturing equipment and skilled workforce despite wartime disruptions. Richter understood the strategic implications immediately. German intelligence reports emphasized British industrial chaos under bombing campaigns. Factories operating with inexperienced workers, production quality declining under pressure to increase output. Yet the Merlin components demonstrated manufacturing precision that required dedicated tooling, skilled machinists, and systematic quality control. The British maintain industrial discipline despite bombing raids that destroy their cities. Richter said quietly, his analytical mind forced toward conclusions that complicated comfortable assumptions. Their manufacturing capabilities exceed our intelligence estimates. This engine represents systematic industrial achievement, not desperate wartime improvisation. The supercharger impeller presented the most technically sophisticated component for analysis. Cast from aluminum alloy and machined to aerodynamic perfection, the impeller blades demonstrated compound curves that optimized air compression at rotational speeds approaching 28,000 revolutions per minute. Each blade had been individually balanced to eliminate vibration that would destroy bearings at operational speeds. Bauer examined the impeller under magnification, noting the surface finish that indicated precision machining rather than simple casting. The blade profiles matched theoretical aerodynamic designs that Richter had seen only in advanced German research programs. The British had translated theoretical fluid dynamics into practical manufacturing, creating supercharger components that exceeded Luftwaffe production standards. The impeller blade profiles demonstrate sophisticated understanding of compressible flow dynamics, Bauer reported, his engineering training recognizing achievements that transcended national boundaries. The British have manufactured components that require 5-axis machining and careful quality control. This level of precision suggests advanced manufacturing capabilities. Richter calculated supercharger efficiency based on impeller geometry and operating parameters. The centrifugal compressor achieved approximately 75% isentropic efficiency, comparable to the best German supercharger designs. But the British had manufactured these components at production rates that suggested industrial capabilities far beyond German intelligence estimates. The British produce approximately 1,000 Merlin engines monthly across multiple factories, Richter calculated, extrapolating from intelligence reports and component serial numbers. This production rate, combined with manufacturing precision we observe, indicates systematic industrial organization that challenges our assumptions about Allied manufacturing chaos. The connecting rod analysis revealed design choices that prioritized reliability over theoretical elegance. Forged steel H-section rods, carefully machined and shot-peened for fatigue resistance. Large end bearings running on replaceable shells rather than direct, crank journal contact. Small end bearings using bronze bushings that could be replaced during routine maintenance. Every design decision emphasized operational durability and field maintainability. German connecting rod designs emphasize weight reduction through aggressive material removal, Bauer observed, comparing British and German approaches to reciprocating component design. The British accept slightly higher component weight in exchange for increased fatigue resistance and easier maintenance. Different engineering philosophies revealing different operational priorities. Richter nodded, understanding the strategic thinking behind British design choices. Luftwaffe doctrine emphasized technical sophistication and pilot skill. Engines were maintained by specialist technicians in well-equipped workshops. Component replacement required careful fitting and precise adjustment. The German approach assumed peacetime workshop conditions would continue during wartime operations. British engines appear designed for maintenance under field conditions by average mechanics, Richter explained, his professional analysis revealing Allied strategic thinking. Replaceable bearing shells eliminate precision fitting requirements. Simplified accessory drives reduce adjustment complexity. The British have engineered for operational sustainability rather than theoretical performance optimization. The valve train components demonstrated British commitment to long-term reliability despite weight penalties. Sodium-cooled exhaust valves that maintained material properties at temperatures exceeding 700 degrees Celsius. Valve springs made from high-grade steel that resisted fatigue through millions of compression cycles. Rocker arms running on needle bearings that eliminated wear and friction losses. Each exhaust valve contains metallic sodium sealed inside the hollow stem, Bauer reported after sectioning a valve for internal examination. The sodium melts at 98 degrees Celsius, creating a liquid that transfers heat from valve head to stem through convective circulation. This internal cooling permits higher exhaust gas temperatures without valve failure. Richter calculated thermal benefits of sodium-cooled valves. The internal heat transfer reduced exhaust valve temperatures by approximately 100 degrees Celsius compared to solid valves. Lower temperatures meant reduced thermal stress, longer component life, and ability to operate at higher power outputs without premature failure. Sophisticated thermal engineering that German designs had not matched in production engines. The British have solved exhaust valve thermal management through materials engineering rather than external cooling, Richter observed, his respect for British technical achievement growing despite ideological resistance. This solution adds manufacturing complexity but provides operational benefits that justify additional cost. The fuel system components revealed British commitment to mixture quality despite using conventional carburetor technology. Twin SU carburetors, each feeding 6 cylinders through carefully designed intake manifolds. Fuel metering jets calibrated for precise mixture ratios across the operational envelope. Automatic mixture control that adjusted fuel flow based on altitude and manifold pressure. Bauer disassembled the carburetors, examining internal components that demonstrated manufacturing precision despite relatively simple mechanical principles. The float chambers maintained consistent fuel level through carefully calibrated inlet needles. The throttle butterflies moved through precision ground bores that eliminated air leaks. Every component reflected careful attention to mixture quality and operational reliability. The carburation system achieves mixture uniformity within 5% across all 12 cylinders. Bauer calculated from intake manifold geometry and flow testing. The British have optimized carburetor, location and intake manifold design to ensure even fuel distribution despite conventional technology. Richter understood that German direct fuel injection provided superior mixture control under certain conditions. But the Merlin's carburation demonstrated that properly engineered conventional technology could achieve mixture quality adequate for high-performance operation. The British had prioritized manufacturing simplicity and field maintainability over theoretical sophistication. Our fuel injection systems require skilled technicians for adjustment and maintenance, Richter admitted, his professional honesty demanding objective comparison. British carburetors can be serviced by average mechanics using common tools. Operational sustainability versus technical sophistication. Different engineering philosophies serving different strategic requirements. The cooling system analysis revealed British thermal engineering that maximized heat rejection while minimizing aerodynamic penalties. Ethylene glycol coolant, pressurized to 15 pounds per square inch, circulated through passages cast directly into cylinder blocks and heads. The radiator, designed for installation beneath the Spitfire's wing, used glycol's superior thermal properties to achieve compact dimensions that reduced drag. The pressurized cooling system permits coolant temperatures approaching 120 degrees Celsius without boiling. Bauer calculated from pressure relief valve specifications. Higher operating temperatures reduce radiator size requirements while improving thermal efficiency. The British have optimized their cooling system for minimum installation drag. Richter understood that German engines typically operated at lower coolant temperatures with larger, less efficient radiators. The British had accepted higher system pressures and temperatures to achieve thermal management that reduced aerodynamic drag. Another design choice that prioritized operational effectiveness over conservative engineering practice. The lubrication system demonstrated British understanding that engine reliability depended on maintaining oil film strength under extreme operating conditions. Separate pressure and scavenge pumps ensured continuous circulation. Oil cooler integrated into the cooling system maintained lubricant temperatures within optimal range. Pressure relief valves protected bearings from excessive loads during cold starts. The lubrication system includes dedicated oil jets for connecting rod bearings, Bauer observed, tracing oil passages through the crankcase. Pressurized lubrication ensures oil film maintenance even during violent combat maneuvers. German engines rely partially on splash lubrication that can be disrupted under sustained G-loads. Richter assembled metallurgical findings into preliminary conclusions that challenged comfortable assumptions about British industrial capabilities. Superior aluminum alloys that permitted higher operating temperatures. precision manufacturing that maintained tight tolerances, despite wartime production pressures. Design choices that prioritized operational reliability and field maintainability over theoretical performance optimization. The British have demonstrated engineering sophistication that equals or exceeds German capabilities in critical areas, Richter wrote in his expanded technical report. Material science, manufacturing precision, and thermal management all represent achievements that challenge our assumptions about Allied industrial limitations. Bauer compiled performance specifications that documented Merlin capabilities with mathematical precision. 1,310 metric horsepower at 3,000 rpm, specific output of 48.5 horsepower per litre, power-to-weight ratio of 2.01 horsepower per kilogram. Every metric favoured the British engine compared to the DB601's specifications. The British achieve superior power density through higher rotational speeds, superior materials, and more efficient thermal management, Bauer summarized, his calculations eliminating ideological interpretation. Their engine weighs 150 kilograms less than our DB601 while producing equivalent power. This 30% advantage in power-to-weight ratio directly impacts fighter aircraft performance. Richter understood the tactical implications. Fighter aircraft performance depended critically on thrust-to-weight ratio. A lighter engine meant either improved acceleration and climb rate or additional payload capacity for fuel and weapons. The Spitfire's Merlin provided both advantages simultaneously through engineering sophistication that German industry had not matched. But the most uncomfortable revelation awaited flight testing. Richter had analysed the engine on the test bench, documenting British engineering achievements in materials, manufacturing, and thermal management. Now the captured Spitfire would fly, and German test pilots would measure actual performance against Luftwaffe intelligence estimates. Static analysis suggested uncomfortable truths. Flight testing would confirm or refute those implications. June 3, 1940. Hauptmann Hans-Werner Lurcher settled into the captured Spitfire's cockpit with professional detachment that had kept him alive through evaluations of 63 different aircraft types. Rechlin's chief test pilot approached enemy fighters with scientific curiosity rather than nationalistic prejudice. His flight reports documented performance with mathematical precision, regardless of whether results confirmed or contradicted Luftwaffe assumptions. The Spitfire cockpit reflected British design philosophy that prioritized pilot efficiency over mechanical complexity. Controls, arranged for intuitive operation. Instruments grouped by function rather than installation convenience. Throttle quadrant positioned for natural hand movement. Every design choice emphasized reducing pilot workload during combat stress. Lurcher examined the engine controls with particular attention. Single throttle lever controlling both power and mixture. Constant speed propeller that automatically adjusted blade angle for optimal efficiency. Radiator flap control that managed cooling without pilot intervention during routine operations. The British had automated systems that German doctrine expected pilots to manage manually. Engine start procedures revealed British engineering priorities. Electric starter motor eliminated hand cranking that risked injury. Automatic priming system injected fuel directly into cylinders for reliable cold starts. The Merlin caught on the third blade rotation, settling into the distinctive burble that resulted from uneven exhaust pulse intervals. Lurcher advanced the throttle carefully, feeling the Spitfire surge forward with authority that exceeded his experience in comparable German fighters. The Merlin responded instantly to throttle inputs without the hesitation that plagued some Daimler-Benz installations. At 90 knots indicated airspeed, Lurcher rotated the Spitfire off Rechlin's grass runway with control harmony that felt immediately familiar despite unconventional aircraft configuration. The climb test would provide definitive performance data. Lurch established steady climb at 160 knots, monitoring cylinder head temperatures and oil pressure as the Spitfire ascended toward operational ceiling. At 3,000 meters altitude, where Messerschmitt performance began degrading noticeably, the Merlin maintained full power through supercharger boost that German single-stage systems struggled to match. Rechlin control, Spitfire test aircraft passing 5,000 meters, climb rate still 500 meters per minute, Lerche transmitted, his voice carrying professional amazement that ground controllers detected despite radio static. British engine maintains sea-level manifold pressure. Through altitude range, where our fighters experience 20% power loss, German doctrine assumed effective fighter combat occurred below 6,000 meters altitude. Yet the Spitfire continued climbing with undiminished performance toward altitudes where Luftwaffe interceptors struggled to operate. The Merlin's single-stage supercharger, driven through its hydraulic coupling, maintained optimal boost pressure across altitude ranges that required two-stage supercharging in German thinking. At 7,000 meters altitude, Lerche leveled the Spitfire and began systematic performance evaluation. The Merlin maintained military power settings without cylinder head temperature excursions that would force German pilots to reduce throttle. Oil pressure remained steady despite reduced atmospheric pressure. Every system reflected British engineering that prioritized high-altitude operations. The speed runs confirmed performance figures that Luftwaffe intelligence had attributed to British propaganda. At military power settings, the Spitfire achieved 570 km per hour true airspeed at optimal altitude, approximately 40 km per hour faster than Messerschmitt Bf 109 Emil variants. More importantly, the British fighter maintained this performance through broader altitude range than German designs. Lerche's radio crackled with instructions from Richter's evaluation team, Spitfire test aircraft, evaluate sustained combat power at altitude, monitor engine temperatures during extended high-power operation. The request carried implications both pilot and engineers understood. German engines frequently overheated during sustained combat maneuvering, forcing pilots to reduce power or risk catastrophic failure. If British engines maintained temperature control during extended high-power operations, they provided tactical advantages that skill alone could not overcome. Lerche held the Spitfire at military power for 15 minutes, monitoring instrument readings that challenged German assumptions about British thermal management. Cylinder head temperatures stabilized at acceptable levels. Oil temperature remained within normal operating range. The cooling system maintained thermal equilibrium despite power outputs that would overheat comparable German installations. Engine temperatures remain within operating limits during sustained high-power operation, Lerche reported, his professional assessment documenting British engineering achievement. Cooling system provides adequate heat rejection without requiring pilot intervention or power reduction. British thermal management exceeds our current capabilities. The maneuverability evaluation revealed performance characteristics that explained Luftwaffe pilot reports about Spitfire turning ability. Lerche rolled the British fighter into maximum rate turn, feeling control loads that remained manageable even at high load factors. The Spitfire circled inside turning, radius that would be impossible for Messerschmitt pilots without risking departure from controlled flight. Maximum sustained turn rate approximately 18 degrees per second at 4,000 meters altitude. Lerche calculated from instrument readings and his internal sense of angular velocity. Turning radius approximately 280 meters. British fighter demonstrates superior maneuverability compared to Bf 109 at combat weights and altitudes. Richter listened to Lerche's transmissions from Rechlin's control tower, understanding that flight testing confirmed uncomfortable conclusions from metallurgical analysis. The British had not merely built competent aircraft engines, they had created propulsion systems that exceeded German designs in power density, high-altitude performance, thermal management, and operational reliability. The dive acceleration test would measure one of the few remaining areas where German intelligence claimed superiority. Messerschmitt. Pilots reported that Bf 109 fighters could accelerate away from pursuing Spitfires through superior dive performance. If true, this advantage might offset British superiority in other performance categories. Lerche rolled inverted and pulled the Spitfire's nose toward Earth, watching airspeed increase past 500 km per hour indicated. The acceleration felt impressive, but not exceptional compared to German fighter dive performance. At 550 kilometers per hour, Lerche attempted to follow through with negative G maneuver that would test British carburetor limitations. The Merlin coughed once as Lerche pushed forward on the control column, then recovered as he relaxed pressure. The negative G fuel starvation that German pilots exploited during combat appeared manageable rather than catastrophic. British pilots would lose perhaps 1 second of pursuit during abrupt nose-down maneuvers. Tactical disadvantage, certainly, but not the decisive weakness that Luftwaffe intelligence had emphasized. British carburetor system experiences momentary power interruption under sustained negative G loads, Lerche reported with clinical precision. Effect duration approximately 1 second, insufficient to provide reliable escape technique against skilled opponents. German fuel injection advantage exists, but should not be overestimated. The landing approach demonstrated British design priorities that emphasized pilot safety over performance optimization. Tricycle landing gear eliminated ground loop tendencies that killed inexperienced German pilots during training. Stall characteristics provided clear warning through control buffet before departure from controlled flight. The Spitfire touched down at 130 km per hour, with docile handling that forgave pilot errors. Lerche completed his post-flight inspection with professional thoroughness that had earned him legendary status among Rechlin's engineering staff. The Merlin showed no signs of distress despite sustained high-power operation at altitude. Oil consumption remained within normal limits. Cylinder compression tested within specifications. The British engine had performed flawlessly throughout evaluation flight, lasting 90 minutes. Richter met Lerche in Rechlin's operations building. Leather notebook ready to record verbal observations that supplemented instrument data. The test pilot's assessment would determine whether laboratory analysis translated into operational advantages during actual flight conditions. The British fighter demonstrates performance that equals or exceeds our Bf 109 across most operational categories, Lerche began, his professional reputation demanding honest assessment regardless of ideological implications. Superior climb rate, better sustained turn performance, adequate high-altitude capability, and reliable engine operation throughout the flight envelope. Richter recorded specifications that confirmed his metallurgical analysis. The Merlin's superior power-to-weight ratio provided exactly the performance advantages that thermodynamics predicted. British engineering sophistication had translated laboratory achievements into operational capabilities that challenged Luftwaffe tactical assumptions. The negative G advantage we possess through fuel injection provides perhaps 1 second escape opportunity during combat, Lerche continued, his combat experience providing context for technical performance. Skilled British pilots can minimize this disadvantage through tactical awareness. Our intelligence assessments have overestimated the operational significance of carburetor limitations. Bauer compiled flight test data into performance curves that documented Spitfire capabilities with mathematical precision. Maximum speed versus altitude, climb rate versus weight, turn radius versus airspeed. Every graph revealed British fighter performance that matched or exceeded Messerschmitt Bf 109 capabilities across operationally relevant conditions. The British achieve superior performance through lighter engine installation and more efficient high-altitude operation, Bauer summarized, his calculations eliminating subjective interpretation. Their Merlin engine provides approximately 30% better power-to-weight ratio than our DB601, resulting in improved acceleration, climb rate, and sustained turn performance. Richter assembled findings into comprehensive technical report that would reach Reichsluftfahrtministerium within 72 hours. 4 weeks of systematic analysis had documented British engineering achievements that challenged fundamental assumptions about Allied industrial capabilities. The Merlin engine represented sophisticated design that exceeded German performance in critical categories, despite smaller displacement and lighter weight. June 28, 1940. Richter presented his findings to Oberst Heinrich Bauer, Rechlin's technical director, in the facility's conference room. Senior Luftwaffe engineers filled chairs around the oak table, men who had built careers on assumptions about German technical superiority. Richter's analysis would challenge comfortable beliefs with uncomfortable facts. British Merlin engine demonstrates power density that exceeds our DB601 by 30%, Richter began, opening his technical report to performance comparison tables. Specific output reaches 48.5 horsepower per litre compared to 39.8 for our engine. This advantage results from superior materials, higher rotational speeds, and more efficient thermal management. Oberst Bauer examined specifications with visible skepticism. German aviation doctrine assumed technical superiority across all domains. Intelligence reports emphasized Allied numerical advantages while dismissing enemy equipment as inferior copies of German innovations. Richter's analysis suggested that British engines matched and possibly exceeded German designs in critical performance categories. Higher rotational speeds reduce engine operational life, Bauer countered, seeking technical explanations that preserved assumptions about German superiority. British engines achieve temporary power advantages through aggressive operating parameters that will result in premature failure under sustained combat conditions. Richter anticipated this objection through 4 weeks of systematic testing. Our analysis included endurance testing at sustained high-power settings. The Merlin maintained thermal equilibrium and acceptable wear rates during 90-minute flight test profile. British engines appear designed for operational durability, despite high-speed operation. The metallurgical analysis revealed British material science that matched German peacetime standards despite wartime production pressures. Aluminum alloys with superior thermal conductivity, precision forgings that maintained dimensional tolerances within hundredths of millimeters, manufacturing quality that suggested systematic industrial organization rather than desperate improvisation. British manufacturing capabilities exceed our intelligence estimates, Richter continued, his professional integrity demanding objective assessment. Component precision, surface finish quality, and material properties all indicate sophisticated industrial processes operating under disciplined quality control. We must revise our understanding of Allied production capabilities. Lurch's flight test report contradicted Luftwaffe tactical assessments that had guided combat doctrine throughout the Battle of France. German pilots reported Spitfires as inferior to Messerschmitts in speed and climb performance. Yet, systematic flight testing demonstrated British fighter superiority across most operational categories. Either Luftwaffe pilots misinterpreted combat experiences, or intelligence processing distorted field reports to match predetermined conclusions. Flight testing confirms British fighter performance equals or exceeds Bf 109 capabilities, Lurcher reported, his combat experience providing credibility that engineers alone could not command. Superior climb rate, better sustained turn performance, and reliable high-altitude operation. Our tactical advantages result from pilot training and combat doctrine, not aircraft superiority. Bauer reviewed climb rate comparisons that documented British performance advantages with mathematical precision. The Spitfire climbed to 5,000 meters altitude, approximately 90 seconds faster than the Messerschmitt Bf 109 Emil. At 7,000 meters, the British fighter maintained 500 meters per minute climb rate, while German performance degraded to 350 meters per minute. These performance figures suggest British fighters can dictate combat engagement altitudes, Bauer admitted, his tactical training recognizing operational implications. If Spitfires climb faster and maintain better high-altitude performance, they control the vertical dimension of air combat. German pilots cannot force engagements at altitudes favorable to our aircraft. Richter understood that technical superiority meant nothing if strategic doctrine prevented effective employment. German fighter tactics emphasized diving attacks from superior altitude, using gravity and accumulated speed to achieve temporary energy advantages. But if British fighters climbed faster and operated more effectively at high altitude, they would occupy the superior position before German formations could achieve tactical advantage. The strategic assessment challenged assumptions that guided Luftwaffe procurement and operational planning. Germany had invested enormous resources, developing fighters optimized for diving attacks and rapid disengagement. This tactical doctrine assumed German aircraft could achieve and maintain altitude advantage through superior climb performance. British Merlin engines demonstrated that assumption no longer held true. British aviation industry has produced engines that exceed our capabilities in power density, operational efficiency, and high-altitude performance, Richter concluded, his final assessment carrying implications that extended far beyond single-engine evaluation. This achievement suggests systematic Allied engineering sophistication that challenges our understanding of relative industrial capabilities. The uncomfortable silence that followed Richter's presentation reflected institutional resistance to conclusions that demanded strategic reassessment. German military doctrine had assumed technological superiority since rearmament began in the mid-1930s. Intelligence agencies had filtered reports through ideological assumptions that dismissed Allied capabilities. Richter's systematic analysis could not be easily dismissed as defeatist propaganda or technical incompetence. Oberst Bauer closed the technical report, his expression revealing professional soldier recognizing uncomfortable truths about battlefield effectiveness. Production recommendations for engine improvements? He asked, seeking practical responses to strategic problems. Richter anticipated this question through weeks of technical analysis. British advantages result from cumulative engineering decisions across multiple systems. Material science, manufacturing precision, thermal management, and design philosophy all contribute to superior performance. Matching British capabilities would require comprehensive industrial reorganization that current circumstances cannot support. The honest assessment carried implications that neither Richter nor Bauer could explicitly acknowledge. Germany lacked the industrial resources, manufacturing capacity, and time necessary to develop engines that matched British Merlin performance. Luftwaffe fighters would operate with propulsion systems inferior to Allied designs throughout the coming conflict. Tactical doctrine and pilot skill would have to compensate for technical disadvantages that engineering alone could not overcome. Bauer authorized expanded production of existing DB6-01 variants with minor improvements that manufacturing capacity could accommodate. Improved supercharger efficiency, better materials for exhaust valves, enhanced cooling system capacity, incremental changes that would narrow but not eliminate British performance advantages. We cannot match British power density without comprehensive engine redesign requiring 2 to 3 years development time, Bauer concluded, his strategic assessment recognizing constraints that ideology could not overcome. Current circumstances demand we maximize existing designs while accepting performance limitations compared to Allied engines. Richter filed his technical report with Reichsluftfahrtministerium Technical Intelligence Section, knowing the document would generate institutional resistance from commanders invested in assumptions about German superiority. Some would dismiss his findings as defeatist propaganda, others would question his methodology or challenge his conclusions. But the Merlin engine sat in Rechlin's workshop, physical evidence that could not be explained away through ideological preference. The captured Spitfire flew 23 additional evaluation missions over subsequent months, providing Luftwaffe pilots with familiarization training against British fighter capabilities. Each flight confirmed Richter's technical analysis. The Merlin engine performed reliably across all operational conditions. British fighter demonstrated performance that matched or exceeded German designs. Allied aviation had achieved engineering sophistication that challenged comfortable assumptions about predetermined technical superiority. September 9, 1940. Richter stood in Rechlin's workshop as mechanics prepared the captured Spitfire for another evaluation flight. 3 months had passed since his initial analysis documented British engineering achievements. Luftwaffe intelligence had filed his report alongside dozens of similar assessments that complicated official narratives about German invincibility. The Battle of Britain raged across the English Channel, where Messerschmitt pilots encountered Spitfires in numbers that exceeded pre-war intelligence estimates. German fighter tactics emphasized diving attacks and rapid disengagement, exploiting the brief advantage fuel injection provided during negative G maneuvers. But British pilots adapted through training and tactical awareness, minimizing German technical advantages while exploiting their own superior high-altitude performance. Richter's analysis had predicted these tactical dynamics with uncomfortable accuracy. British fighters could not follow German dives without momentary power loss, but Spitfires climbed faster, turned tighter, and operated more effectively at high altitude. The technical advantages balanced differently than Luftwaffe doctrine had anticipated. Air combat became contest between matched opponents rather than technological mismatch favoring German superiority. Casualties mounted on both sides as summer progressed toward autumn. Luftwaffe pilots respected Spitfire capabilities in ways that contradicted pre-war propaganda about Allied inferiority. British fighters proved difficult to surprise, harder to escape, and capable of sustained combat at altitudes where German performance degraded. The Merlin engine provided exactly the operational advantages that Richter's metallurgical analysis had documented. By late September, Luftwaffe strategic bombing campaigns shifted from daylight operations to night attacks, tacit admission that German fighters could not achieve air superiority over southern England. The decision reflected tactical reality that Richter's technical analysis had foreshadowed. When the enemy builds engines that exceed your own in critical performance categories, numerical superiority alone proves insufficient for operational success. Richter never learned whether his technical report influenced Luftwaffe strategic planning. Military organizations rarely acknowledge when field intelligence contradicts comfortable assumptions, but the captured Merlin engine represented physical evidence that German aviation had encountered an opponent whose engineering capabilities matched or exceeded their own. That uncomfortable truth would shape the air war throughout subsequent years of conflict. The British continued developing Merlin variants that increased power output through two-stage supercharging and improved materials. By 1943, late-model Merlins produced over 1,800 horsepower, nearly 50% more than the engine Richter had analyzed in 1940. American factories manufactured 55,000 Packard-built Merlins that powered P-51 Mustangs to strategic victories over German industrial centers. German engine development pursued parallel improvements with mixed success. Daimler-Benz created DB605 variants that approached 2,000 horsepower through exotic fuel injection and boost systems. But German engines never achieved the power density or operational reliability that characterized British designs. Material shortages, manufacturing constraints, and strategic bombing disrupted German aviation industry throughout the war's final years. Richter survived the war, his technical reputation intact despite analyzing uncomfortable truths about Allied capabilities. Post-war technical historians recognized his Rechlin report as one of the most accurate contemporary assessments of British aviation engineering. His systematic analysis had documented Merlin engine achievements with scientific precision that ideology could not corrupt. The captured Spitfire remained at Rechlin until April 1945, when advancing Soviet forces captured the facility. The aircraft disappeared into intelligence archives, but the technical lessons Richter documented continued influencing aviation engineering long after the conflict ended. The Merlin engine had demonstrated that systematic engineering excellence could overcome theoretical disadvantages through superior materials, precision manufacturing, and operational reliability. Modern aviation historians recognize the Rolls-Royce Merlin as one of the most successful aircraft engines ever designed. Over 167,000 Merlins powered 40 different aircraft types throughout the Second World War. The engine's power density, reliability, and development potential established design principles that guided piston engine development for decades afterward. But in June 1940, Klaus Richter stood in Rechlin's workshop examining captured British technology that challenged his understanding of Allied capabilities. The Merlin engine represented more than sophisticated hardware. It embodied British industrial determination to match German technical achievement through systematic engineering excellence. That realization, documented in 4 weeks of careful analysis, provided uncomfortable preview of strategic competition that would decide the air war's outcome. Wars are won through accurate understanding of enemy capabilities, not comfortable delusions about predetermined superiority. Richter's technical report documented that truth with mathematical precision that transcended ideology. The Merlin engine exceeded German designs by approximately 500 horsepower, when accounting for power-to-weight advantages and high-altitude performance. That engineering achievement, multiplied across tens of thousands of aircraft, helped determine the conflict's ultimate resolution. The British had not won through industrial accident or technological luck. They had systematically developed engines that maximized power density through higher rotational speeds, superior materials, and efficient thermal management. They had manufactured these engines with precision that maintained quality standards despite bombing raids and resource constraints. They had created propulsion systems designed for operational effectiveness rather than theoretical perfection. German engineering had pursued different priorities that emphasized displacement, moderate speeds, and theoretical elegance. Both approaches represented valid engineering philosophies serving different strategic requirements. But when measured by operational effectiveness in sustained air combat, British design choices proved superior. The Merlin engine demonstrated that truth through performance that exceeded German designs across categories that determined fighter effectiveness. Richter's analysis provided German leadership with accurate technical intelligence regarding Allied capabilities. Whether that intelligence influenced strategic planning remained classified within military archives that survived the war, but systematic evaluation of captured enemy technology represented essential function of military intelligence, regardless of whether conclusions confirmed or contradicted ideological preferences. The captured Merlin engine sat in Rechlin's workshop for 5 years, teaching Luftwaffe engineers uncomfortable lessons about Allied industrial capabilities. Some lessons were learned, others were ignored, but the British engine remained, physical evidence that could not be explained away through comfortable assumptions about predetermined technical superiority. That evidence, systematically analyzed by engineers like Klaus Richter, documented truths that helped shape aviation history's most consequential conflict. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.